And so you can't prevent it entirely. What you can do is to reduce it to a level where it's not a serious problem. And I'm going to tell you how to do that. There are sort of Star Wars crazy things you can do that are really expensive and really time consuming and a pain in the neck. And I'm not going to recommend those because if you follow what I consider to be fairly simple standard practice things that are relatively inexpensive, you can eliminate most problems. Now before we do that, let's talk about where PCR contamination comes from. Let's suppose that my lab studies the TPR gene in mouse and we study TPR gene expression. We're a TPR lab, okay? Well, that means in my lab I have mouse genomic DNA because we work on mouse. It would mean that I have total RNA in the lab from mouse. It would mean that I have probably messenger RNA in the lab from mouse. I've probably made cDNA in the lab from mouse, just like we've done in this course, right? Worst of all, because I study TPR, I've probably done a lot of PCR on the TPR gene or on TPR mRNA looking at expression. So, okay. PCR product is a huge problem because every time you do PCR, you make a ton of product. You make a ton of product of exactly the thing that you're studying. And so PCR becomes a real major source of contamination, much worse than any of these other things. So they're all problematic, but PCR is the worst, right? Because you're making a lot of product of the exact thing that you're worried about in terms of contamination. So think about your RT-PCR reaction you ran the other day on TPR. Well, why didn't you have contamination? You're working in a lab, in a teaching lab that doesn't do mouse, right? None of the teaching labs use mouse in our here at Smith. And so no chance of contamination from mouse. Nobody studies TPR in there. In fact, nobody's done TPR in that lab since the year before, right? When we taught summer course last year. So the lab that you're working in is a great place to do the PCRs on the various experiments you're doing because nobody's done that sort of work in there since last summer, and the lab's been cleaned a million times since then. But if your lab studies TPR or my lab studies TPR, my lab is the most likely lab in the entire world to be contaminated with TPR. Now, where do you find, for example, TPR product in a lab where you're doing PCR, gene expression, etc.? And the answer is everywhere. The answer is it's everywhere. So a colleague of mine, I mentioned that PGK2 gene from mouse a while ago. A colleague of mine works on PGK, has in the past. And I visited his lab once, and they were having a contamination problem. So we decided to do a fun little thing. We went around the lab and we did swabs, on various places in the lab, knobs on instruments, the telephone, the floor, the wall, the ceiling, all over the place. And everything got positive. I mean, the whole lab. So it gets around. And how does it get around? Well, it gets around on aerosols. Every time you open a tube, you generate a small aerosol. You don't see it. You don't know it's there. But you are generating a small amount of aerosol that gets on dust particles, gets on gloves, gets on clothing, and it moves around the lab. And it gets everywhere. So you can't avoid that. That's going to happen. So what can you do to prevent getting your reaction contaminated? That's really the issue. This, contaminating your lab, that's going to happen, right? But what can you do to prevent your PCR reaction? Okay, so I'm going to go through a bunch of rules or suggestions, let's call them, for how you can prevent contamination. And I'll tell you which rules that we try to follow strictly in my lab. And my lab, I don't know, Nicole, we've had as many as 25 undergrads and grad students and, research associates, a lot of people working in the lab, and contamination really kept to a minimum because we're pretty strict about these rules. So what do? First of all, when you're setting up PCR, be really careful what you touch. You're going to have your pipetters and your tubes for setting up the PCR, and really try not to touch anything else, right? Don't get up and answer the phone, or don't get up and adjust an instrument if your water bath's not set right or something. Sit and do your PCR and don't do anything else, right? Don't touch anything. Don't scratch your arm, right? Your arm is covered with, nucleases and who knows what else, right? And DNA, perhaps from the lab that you were working in. So try not to touch anything except for what you have to touch, right? So a lot of this sort of common sense here. If you do touch something, so you always want to be hyper aware of what you're doing, right? If you do touch something, then change your gloves, right? Better to change your gloves than, in terms of money and in terms of waste, it's better to change your gloves than to ruin a bunch of PCR reactions that you're setting up, right? So change gloves whenever you think it may be necessary. In terms of pipetting, a huge advance was made. I think this was back in the 90s when barrier pipette tips were developed. But the regular tips that we use have no barrier, but for PCR and for some other things, we use these barrier tips that have a plug in them that prevents liquid aerosolizing and contaminating the bore of your pipette. So before these barrier tips, what would happen is you would have your pipetter with the tip on it, and you would pipette up your liquid, and then when you blow your liquid out, if you look carefully, you've all seen this, where the liquid goes out, and there's a little line of a bubble that goes down, and then the bubble pops. And when that happens, then you're getting a big aerosol burst, and that's going to contaminate the bore of the pipetter. And then when you pipette later on with that same pipetter, you're going to get contamination. The barrier tips that we use prevent that from happening, because when you're pipetting, you can't prevent the aerosolization, but the plug prevents the pipetter from getting contaminated. And so when we do PCR, we always use the barrier tips, always, always, always. Okay. So that's an easy one. Along with that one is we use dedicated pipetters. So in our PCR area, there are pipetters that are used for setting up the master mix. That is everything except the template, and that's all those pipetters are used for. So a dedicated set of pipetters. Let me add here, dedicated set of pipettes, and this is for everything except template. So you're using this to pipette in your buffer and your enzymes and your water and your nucleotides, but not template. Now, along with that, if you can, the ideal is to have a room called the pre-PCR room that's used only for setting up master mix for PCR reactions and nothing else. Okay? You'd like this room to be separate. If possible, you'd like it to be on a separate air supply, or at least have, good filters, right? Not everywhere has this, but a lot of places do. Funny story about Ford, our building here, and our pre-PCR area. So when this building was designed, I made sure they designed in a pre-PCR area, right? So a nice pre-PCR room, had a separate air supply, and a door, and it was completely separate. It was away from my lab, across the hall and away. So perfect, really perfect for our purposes. And then when the building was built, they realized that the design wasn't quite right for putting in a door. So it's got everything. It's got the air filtration separate and everything. There's no friggin' door. So, but it's still separate and away from my lab, and it's actually worked out pretty well for us. It's been fine. So isn't 100% necessary to have a separate room. If you can have a separate area that's away from your main lab, that's away from where you're running gels and setting up, running PCRs where your PCR instruments are. If you can have a separate area somewhere else, that's great. That's really optimal. If you absolutely can't do that, if it has to be in the same area as your lab, then please have a PCR area that's sort of in a corner, and maybe you put some tape down and you say no DNA into this area right now. That's not ideal at all, but it's better than nothing. But if you can have a separate room or an area that's separate from your lab, that's really ideal. So this dedicated PCR room would be where your dedicated pipettes are and your barrier tips, and you would have a refrigerator and freezer in there, so all your reagents are there. But what you don't do is allow any DNA into that area, into that room. No DNA. That's the rule. So buffers can be in there, water, et cetera. The only DNA that goes in there is the people, right? And unfortunately, people carry DNA with them, on their clothes and hands and everything. So, labs that are super paranoid that work on ancient DNA, they'll actually have one of those, like, the Centers for Disease Control or whatever, where you go in and take a shower and change clothes and then go in. You don't have to do that, obviously. But if you have this separate area and clean lab coats and people put on a nice lab coat, put on clean gloves, and then go in, you're doing a good job without going to ridiculous means, right? Okay. Now, in that room, if you can, what you would like to have is a hood with UV light. There are PCR hoods that you can buy that aren't terribly expensive, that have filtered air, and they have UV light. And the great thing about UV light is that UV light cross-links within DNA, so it can't be PCR amplified. So what you can do is use the hood inside your PCR area where you set up your reactions. You set up your tubes, again, everything is some template, no DNA allowed in there. You set up everything in there in the hood, your pipettes are in the hood, you bring your reagents out of the refrigerator and freezer into the hood, the refrigerator and freezer with your reagents is already there, right? And when you're through working, you turn on those UV lights and it decontaminates the hood. Now, one thing you have to remember about the UV lights is that it only decontaminates what it can see, right? So if you put pipetters in there, it's only decontaminating the top, right? The other side is, maybe still contaminated. So some people will go in and flip their pipetters over after an hour or two. Probably helpful. You still got the sides that are probably not getting a very good dose of UV, but at least you're doing the best you can. And the best you can is going to take care of most problems. You've got your dedicated area, you've got your dedicated pipetters, you've got your hood with UV. Again, I'm terrible on this. I guessed how much these cost a couple of years ago, and I was really off. So it's more than I thought, but maybe $1,000, and a couple $1,000. You're going to save that, in a pretty short amount of time. The amount of reagents and research time you're going to save by reducing your contamination. Now, in that pre-PCR area, you're going to keep things really clean. And the way you're going to keep things really clean is you're going to use bleach. 10% bleach is ideal. Not all bleach is apparently created equal. And so here in the U.S., we have access to Clorox bleach. You can dilute the Clorox to a 10% bleach solution, and that's ideal. Now, it turns out bleach doesn't last forever, and so you want to make up to 10% bleach frequently, so we do weekly, so we do bleach every week, and you don't buy too much at a time, and then when it runs out, run down to Stop and Shop about bleach is people will spray down their bench with bleach, you know, wait a few seconds and then wipe it down. That's not taking care of most DNA. So bleach, what it does is, again, it causes damage to the DNA that makes it so it can't be amplified. But that takes time. It's not instantaneous. So 15 to 30 minutes has been shown by people who have studied this, that 15 to 30 minutes is ideal. So what you want to do is go in and spray down your area and then go away and have a cup of coffee and then go back, and then you're ready to go. So a little patience goes a long way. I would, you know, hate to make waves, right? But that's really true here. If you're in too big a hurry and you rush ahead and you don't maybe follow all the rules, then your experiment doesn't work and then you've wasted a bunch of time. Now I put not ethanol there because people are used to cleaning benches with ethanol. Ethanol will do a good job at killing microorganisms, but DNA loves ethanol, right? You know, we use ethanol to precipitate DNA. DNA and ethanol get along really well, right? So spraying your bench with ethanol and then wiping it down. Okay, you're going to get rid of some DNA because you wiped your bench down, but it's not as nearly effective as bleach is, right? So bleach is the best. Ethanol, not great. Now, you've done all this in your pre-PCR area. You've set up your PCR reactions. Maybe you've got, we do a lot of PCR in 96-well plates because, you know, we'll do a million PCR reactions. So maybe you've set up 96 reactions in a 96-well plate, and it has all the reagents in there, but there's no template. That room hasn't seen any DNA. Now you take that plate that's got all your reactions in it, you cover it up, and now you go someplace else. You leave the PCR and you go someplace else. Where you go back to my lab. If my lab studies PCR, and now I'm going to go add template, do I want to go out it in my lab? Probably not. That's a bad place, right? It's really contaminated with PCR. If you can, and it's not always possible, take that plate, go to some other space, and add your template there, if you can. Now you're going to say, well, you have your template there, now that space is contaminated, right? And that's true to a certain degree. But the ideal situation is you have one place where you set up reactions, you have your lab where you do everything else, and then maybe you add templates somewhere else if you can. Most people, adding templates somewhere else is just not practical. So what you can do is take it back to your lab, keep things covered, and just add the template as quickly as you can. Keep things covered. You've got your negative controls in there that will tell you if you have a problem. You can go somewhere else, right? Now, in my lab, which is across the hall from where your labs are, often what we'll do is if we're having any contamination issue at all, one thing I'll do is have my students, I'll say, just go across the hall to the teaching lab and set it up there. I'll set it up in our lab. That's kind of a terrible place to do it. And a lot of times that takes care of the problem. Okay, so add the template last, always last, and somewhere else, not your pre-PCR room for sure, because you don't want that room contaminated. All right, the last one is really easy, but really important, and can save you a lot of money. So your PCR reagents, if you do a lot of PCR, that's going to be a major investment in your lab. So my lab does a lot of PCR, and I'll bet, I bet our supply budget is at least 20% PCR reagents. I'll bet a lot, maybe even more than that. So it's going to be a big part of your budget. Each reaction doesn't cost very much, but you do a lot of reactions, it's a lot of money. And so you're buying a lot of PCR reagents, you're getting a lot of the enzyme and the buffers and the DNTPs and all of that, right? So you want to protect your investment as well as possible. You also want to prevent as much as possible if individual A contaminates their stuff, having that not affect everybody else in the lab, right? So what we do is when our PCR reagents come in, somebody in the lab that I really trust aliquots those reagents into separate aliquots, And then person 1 gets an aliquot, person 2 gets an aliquot, person 3 gets an aliquot, and so on. So everybody has their own aliquots of the various reagents. Now, if person 1 contaminates their reagents, it doesn't affect anybody else, right? Everybody else is okay. We detect the contamination in individuals 1 reagents because we see that we have a negative control giving us a positive result. So the first thing we do is throw those reagents away. Now, if this was your main tube of polymerase that you just paid $250 for, you're throwing away $250 maybe on the same day you got it, right? Because somebody contaminated it. But if everybody's got their own little aliquot, then that person throws away their stuff and everybody else is fine, right? So what you want to avoid is everybody using the same tubes to get their reagents, because one person makes a mistake and then it's maybe, you know, if everybody else was setting up reactions on the same day, everybody's stuff is messed up, right? So, really easy to do, really inexpensive, will save you a lot of money and a lot of frustration from various people in the lab, right? I would say that if somebody does it once, you give them a new set of reagents, they do it again, a new set of reagents, they do it again, you put them on a different project. Okay, what's the main concern when you're worried about contaminating your lab? I said if my lab works on PCR, it's going to be contaminated with PCR. But you'd like to keep that to a minimum. You're not going to be able to prevent it completely, but you can tamp it down. You can keep it to a minimum. And one way to do that is if you have a separate hood that you load your gels in. This can save a lot of headache, because what you often do after you run a bunch of PCRs is you open those tubes and you load product on a gel to see if you got a product, right? Well, when you open those tubes, that's when things, you know, go wrong, right? That's when things go sideways, because that's the time when you're going to do the most contamination. And then it's even worse. Not only do you open those tubes, but you suck solution out and you blow it out into another place, and right? So that's the worst when you're dealing with your PCR product, and especially when you're opening up those tubes and loading it into gels. So the answer is you take the tubes out of the PCR instrument and you go to a hood. We have these, again, it can be like one of those PCR hoods or just some old hood that somebody was going to throw away. Just a place that sort of is separate, that you can keep clean and bleach down and keep things a little bit separate. Open the tubes in that hood, load the gels in that hood, and you're not going to completely keep your lab free of contamination, because people have to be working at their benches and pipetting genomic DNA and stuff. But if you open your PCR tubes and you think about it, and you open the tubes in that hood, and you load your gels in that hood, you're going to save a lot of contamination. And if you keep the contamination level down, then that's going to increase your probability of not contaminating reactions later on. So this is really great. So over the years, you know, we've learned these things by experience, right? So when the barrier tips first became available, that was a huge advance. And when that happened, you know, frequency of contamination dropped tremendously. Another huge advance in my lab is when we started loading and running gels in a hood in the lab. We have to run our gels in the lab, we got to run them somewhere. But by doing this, contamination again was reduced significantly. So each one of these things is kind of small, but taken together, you're really going to have a dramatic impact on the rate of contamination that's going to occur in the lab. And again, over the course of a year, you've got a busy lab with a lot of people, it'll happen, but you can really hold it to a minimum this way. And the last thing I want to say is, you always have to run negative controls. If we're setting up a 96 well plate with 96 PCRs, we'll have a negative control as the first well, we'll have a couple negative controls sort of scattered in the middle, and then a negative control at the end. And if you do that, and they're all clean, then you good about is the results, right? When you're doing pipetting, you never know exactly where the contamination is going to occur. So the idea of having one at the beginning, one at the end, and a couple in the middle is really good. If you're doing a bunch, if you're only setting up a few, if you have 10 tubes, then maybe just doing one at the end is fine. But if you're only going to do one negative control, I would do it as the last tube, because that's the one that's most likely to get contaminated because you've been doing all this pipetting. And then some other common sense. When you're pipetting template into your tubes, if you're pipetting template into a series of tubes, don't be pipetting right over the tops of all the other tubes, right? If you're gonna take that template over here and you're gonna add it to a tube, and you've got 10 tubes lined up over here, take the first tube, take it over here and pipette it over here, and then close it up and put it back, and then don't be pipetting right over the tops of all those other tubes, right? So just practical things to think about. Just have your noodle on while you're doing this, and it'll help a lot. I'm always nervous when I see my students with their earphones in and listening to jamming while they're setting up PCR, but they do great. They're better at multitasking than I am, that's for sure. So anyway, so that's what I have to say about that. Any questions? Yeah.